Alright, so in this video we're going to talk about mirrors that are curved. So in the last video we talked about that mirrors reflect light, and that when we have a flat mirror, the angle of incidence equals the angle of reflection. Now in this video we're going to talk about how do we create images and what do they look like and where do they appear when we hold an object in front of a curved mirror. So when this here shows some of the different variables that we have to define in order to predict these patterns. So here is the mirror. So here's a curved mirror. We have both convex and concave mirrors. This is a concave mirror because it bends towards you. A convex mirror bends away from you. So here's the object and then here's the mirror. Now, if we were to extend this curved mirror out, it would eventually make a large circle, right? So C is actually the center of that circle, or the radius of curvature, it's called. And the focal point is actually 1/2 of that radius. Okay, so it's halfway between the center of curvature and the mirror. Now the last thing that we have here is called the principal axis, and the principal axis runs perpendicular to the mirror where it encounters the mirror, and then we place the object in front of that mirror and it produces an image. And here it shows actually where that image lies and what size it is relative to this image. It determines whether it's upside down or right side up. And so in order to predict this, we use both the mirror equation and ray diagrams. So for ray diagrams or the mirror equation, I have them here. It's actually the same for lenses, and I'll talk about how that applies later. So you only really have to memorize one set of rules, but let's just begin by looking at mirrors. So the mirror or lens equation is that 1 over the image position or distance from the mirror plus 1 over the object distance from the mirror is equal to 1 over the focal length. Okay, and this is the lens equation too. The equation's the same. There's a little bit different conventions for signs, like using positive versus negative, and we'll talk about what those are. Now, in order to draw a ray diagram, there's 3 different rays that you draw. The first ray diagram goes from the object parallel to the principal axis and through F. So you see here, this arrow right here is the first object, and here's the mirror, and I've set it over here. And if I draw a ray, I start at the tip of the arrow or the tip of the object, and it goes parallel to the principal axis. So that's what this line is here, running parallel to the principal axis. When it encounters the mirror, it's going to reflect off of the mirror, because that's what light does, and it's going to reflect through F, the focal length point, which is right here. So the second ray then is opposite of that. That goes through the focal length and then, or the focal point, and then reflects off the mirror parallel to the principal axis. So that's the second ray. Starting here at the top of the object, going through F, encountering the mirror, and then bouncing back parallel to the principal axis, which is this line where the C and F are. The last ray then goes from the object through C and back. You really only need 2 rays to draw the image. However, the third one is sort of a check to make sure you did it right. So if I start at the tip of the object, I'm going to go through C and then hit the mirror and bounce straight back. And so we see where all of the reflected rays cross is where the image is going to be produced. And the tip of the arrow would be where those lines cross. You can see that in this case, this concave mirror, placing the object where it is going to make an image that's upside down, and it's a little bit smaller than the object. Now we can actually learn some rules, and this is going to be the same for lenses too, as you'll see. So it'll seem like a lot, but you can just memorize a few conventions and apply it to everything. So some of the rules for mirrors, or thinking about mirrors, is that mirrors are always going to reflect light. That's what they do. So an image that appears in front of the mirror or in the same position or in the same side as where the object is considered real. And in this case, mathematically, if the image distance ends up being positive, then it's going to be real. Whereas if the image appears behind the mirror, then it is considered to be virtual, or if it appears on the opposite side of the mirror as the object, then it's virtual, and the image distance is actually going to be a negative value using the lens equation. Now we can also look at the idea of magnification. In order to calculate magnification, you do the opposite of image over object. If M is positive, then it's upright. If M is negative, then it's inverted. So if we look back at the two previous examples, you can sort of see how this happens. So let me just click back up. And you can see it. Here is an example where we have a ray diagram, right? And you have the object. It's in front of the mirror. It's creating a virtual image because it's behind over here, and it's magnified, it's larger than the object, right? And it's also upright. Whereas if we look at this, you can see that this is an example of a concave mirror creating an inverted image that is smaller than what it appears, or smaller than the object, and it's inverted or upside down. So it's real and it's inverted and it's smaller. Now the magnification is either going to be less than 1 or greater than 1. If it's less than 1, it's smaller. If it's greater than 1, it's bigger. Right? Now, there are videos of me doing many examples of different types of images that are created using both concave and convex mirrors. And so those sample problems, you can go and watch me actually work through them and do the math and apply these ideas. But for now, just make sure you get this stuff written down. So a concave mirror, another convention that we have to know is that for a concave mirror, if you're an object over here and you're looking at the mirror, the focal length is over on this side, right? So we treat the focal length as being positive, right? And in this example, we can actually see the image that is produced. So if we put something in front of a concave mirror, you can see an inverted image, right? Now, for convex mirrors, so that's one that's going to bow away from you, so like a Christmas tree ornament. And in this case, the focal length is actually going to be on the other side. So you're going to be over here, right? You're going to be standing in front of the mirror, but the focal length is going to be over here because the center of curvature is in the middle. It curves this way, right? So we treat the focal point as being negative. Now, how I'm going to teach you how to do this is that don't memorize a lot of conventions. A lot of kids start by saying, all right, if I put an object here, it's going to make an image that looks like this. Or if I put an object in front of the focal length, it's going to make an image that looks like this. Really, if you memorize the conventions, the few rules, and you can draw a ray diagram, then you can use these same rules for every type of mirror or lens that we're going to do. So go ahead and after this video, watch some sample problems as you work through ray diagrams for mirrors in the light homework.